this is actually working. Hi, welcome. We're in Engineering 11. I'll hand back graded exams later today. I have updates for Lab 3, which we'll talk about. Today, I'm really hoping we can put a wrap on Lesson 5, which was focused on fixed point material, or fixed point data representations. The whole concept is to transition from fixed points into IEEE floating points, which we'll get into. All right. So let's do a quick recall. It's been at least 7 days since we saw each other. I think exactly 7 days since we were together last. And last time you all took a test, so it's been a minute since we thought about representations in the learning context. All right, so let's do a recall of the stuff that we've done so far.
You're up.
Yeah? Awesome, thank you so much. All right, so let's think about decimal representations of fractions. And I forget if we had a favorite fraction. 5, yeah, that's a good fraction. We could do 5. How about we do 5/11ths, and why don't we add, I don't know, 316. So 316 and 5/11ths. Can somebody give me that number as a single, what we might call, say, numerator over denominator? I can do that for myself. So let's do 316 times 11 plus 5. So 3481 over 11. And then why don't we go ahead and see what a nice representation of that number would be. Okay, any guesses about what happens there? So let's go ahead and format long. Any guesses? Yeah, repeating all the way to infinity. And what's the repeating nature of it? What's the last part of it? Or 5. Let's go ahead and write this in general decimal format. So what would be the general decimal format of that thing? D2, D1, D0, point, D-1, D-2, D-3, and goes on forever, right? We named these two parts separately. Do you remember what we called the front thing? Yeah. So Ethan says integer part of that thing. What was this called? Yep. Radix point. I think that's what I heard you say. Yep. And then this thing? Yep. In this particular example, is the fractional part infinite or finite? In this particular example. Yeah. Infinite if we want an exact representation. All right, and then what we ended up doing at the last part of the class last time, we actually had this really, really powerful concept. So we partitioned, so we had two theorems or propositions, I don't know what we want to call them today. So proposition 1 from last time. If we have an infinite repeating, what am I about to say? Decimal expansion for y, then so we had this proposition that said that any number that has an infinite repeating string that beyond the radix point will definitely be a rational number. We had another proposition that said if y in Q has a finite exact representation, what we might call decimal expansion, and if it's finite exact, we could say that it has an integer part and also what? Yeah, a fractional part, decimal part, I guess that works too. And that this is an actual exact equality, then what did we say about how we could write y, sorry? Some numerator over a power of 2 times a power of 5 for some j and k in the non-negative integers. So in this case, I'm going to call these type 1 rationals with respect to base 10. Could you guess what we might call these ones? Yeah, not quite irrationals. Yeah, we call these type 2 rationals. With respect to base 10. And then we actually had some notation for this, right? We said to ourselves, like, okay, if we're going to represent these numbers on a computer, one of the sets of numbers, our representation can be exact, depending on how many bits we have, the other one non-exact. So this thing was going to be the set of type 1 rationals for radix 10. Can you guess what the other one's going to be? Yeah. What's another one? What's another way to say these? And I'm not committed to, later in my career, I plan to change this notation. It's just the best I could do with 700 hours of writing that I did in the first 7 lessons, or however long it took. I don't know. It was a 6-month-long project. So this is what we would call finite exact expansion. So fractions that have a finite exact decimal expansion, what would we say about those? Fractions that require an infinite decimal expansion to be what? What's another way to say they require an infinite decimal expansion to be exact? If we take only a finite set of decimal digits after the radix, what's going to happen? Yeah, we'll have error, right? So it will no longer be exactly equal, but instead there will be some approximation error associated with that encoding. Okay, could you guess what we're going to do next? All of this work was done with respect to base 10. Could you guess what the next step is?
Go to binary.
Go to binary. What happens if we map this work to binary? All right, so let's go ahead and do that. I thought I had my little, there they are. All right, could you guess what we call a general binary representation of a fraction? So I guess maybe one of the first things we do is look at an example. And let's start with the example 3 divided by 2. Could you write this as a sum of powers of 2? Okay, what would that look like? Okay, so this is 1 times 2 to the 0 plus 1 times 2 to the negative 1, which in binary representation we might write as 1.1. Another way to write that is b0 dot b negative 1. Could you guess what we call the thing in front? So this is what we would call the integer part. Over here, this is what we would call the fractional part. Okay. All right. You want to take another example, or perhaps intuit the general form? Could you guess what we call the general form on this thing? Good morning.
Fish on those slow days.
I feel it. It's kind of painful.
General
We're not to fixed point yet. What we're doing right now is we're introducing the background behind fixed point, right? So how would I write, what was the general form of the decimal representation?
sum of pi minus 2 to the I.
Yeah, so we had these leading digits in front of the radix points. We said that each digit we called d sub I minus 1. In this case, we had an I plus 1 digit integer part and an f digit fractional part. Could you guess what we would do to change that to binary? Yeah, so literally we would say like, okay, b sub I minus 1, all the way down to b1, b0, point, b negative 1, b negative 2, b negative f. In this case, we would call this what?
That would be the integer part.
Yeah, this is an I plus 1 bit integer part. What about this?
I plus, no, that's just
Yeah,
I bit fractional part.
yeah, it's an f bit fractional part because there's f bits to that number. What is the corresponding decimal representation of that? What do I scale each bit with? Okay, so we're going to go ahead and sum. What's the lower bound of my sum?
Negative f.
Yep. What's the upper bound of my sum?
I.
I, each bit, b sub k, what do I multiply each bit by? 2 to the power of k. This thing is what we would call a finite binary expansion or representation how many bits does that binary representation have? How many bits are in the fractional part? F. How many bits are in the integer part? I plus 1. So how many total bits are there? Yeah, I plus 1 plus f bits. I guess I should write the parentheses on the outside of that thing. Okay. So here's a challenge for you. I'd like you to do the following two for me. So I want you to find So I'm going to put these examples up for you. So if I set y equals 19 over 8, please find the corresponding binary representation of that number. And then also, for example 3, I'm going to go ahead and set, I think you all said that you like it when I do stuff that's not in the notes, right? It's been to something like, okay, so let me just make this one off the top of my head. 923 divided by 128. Yeah. 1,923 divided by 128. So go ahead and turn these things into the corresponding binary representations. You can use MATLAB if you'd like. So I'll do looks like maybe I should do the first one first, right? Why don't we call it method 1? So let's do method 1. Power decomposition. Could you write the powers of 19 for me? Powers of 2 involved in 19? No? So 19 is definitely 16 plus 2 plus 1, right? Which in this case would be 16 over 8 plus 2 over 8 plus 1 over 8. What's 16 over 8? 2. 2 over 8? Oh, 1/4? 1 over 8? Okay, could you write that in powers for me? 2 to the first plus 2 to the negative 2 plus 2 to the negative 3. Okay, so what would that look like? One 0.011. So that was method 1. Okay, I want to show you method 2. Make the point float left. I want to start using float so that you have a sense of what the hell I'm talking about. What is 19 in binary? (16 plus 2 plus 1), which is what? 2 to the 4th plus 2 to the 1 plus 2 to the 0. How would I write that in binary? 1, 1. Second power has 0. Third power has 0. Fourth power has 1. Okay. What is the number 8 in binary? Yeah, it's 2 to the 3rd, which is what? 0 first power, 0 second power, 1 third power, which immediately implies that 19 divided by 8, well, this would be 1, 0, 0, 1, 1 divided by 1, 0, 0. And remember, this is a binary division. But let me ask you this. In decimal, if I divide by 100, what do I do? Must be that case, right? 0th power, first power, second power, third power. Should be 3 zeros there, right? What do I do when I divide by 100 in binary? In decimal? Dunk, 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 dunk. I just move it to the left, right? Okay, well, where is the radix in the numerator? It's an unwritten radix right there, right? Because the 0 mark is after that number. If I divide by 1,000, what would I do with that radix? I would literally just shift the radix left how many points? So it's like a little float, right? Dunk, dunk, dunk. What do you notice about those two numbers? Okay. What does it mean to float a radix down the string of bits? Oh, this is fun. To move it. It moves around, right? What would it mean to fix the radix? Keep it in the same thing. So what is a fixed point representation? The decimal point doesn't move positions. So in a fixed point representation, decimal point stays exactly where it started, right? What is a floating point representation? The point floats around the string of bits depending on where it needs to be to represent that number, right? Okay, let's try another one. So those are two different methods to do the same one. One of them is via power representation. The other one is by floating downwards. I would like you to finish on your own this problem. Anybody finished with this already? Okay. If you finished with this already, I want you to state what the theorem you think is for which numbers have... Here is a better way to do this. Go ahead and find the binary representation of, I don't know. You said you want me to make stuff up, right? Okay. I don't want to be too brutal. Let's start with something easy. assuming that you did well on your test, maybe we can use MATLAB. I'm not sure. I think it looks something like this. 1, 2, 3, 4, 5, 6, 7. Yeah? I mean, we could check this, right? So 1923 divided by 128 is going to be 15. Indeed, those first ones are 15. And then it looks like I got 3 over 128, right? Yeah, those are the same number. Okay, so let's try to look at this one. So 529 over 5. So 529 divided by 5. And then let's go ahead and format bank. So the claim is going to be format bank is used for money, right? So this is going to be 105.8. Okay. Any suggestions on how I convert that thing? I don't know if I did that in these ones, did I? Well, the front part is not bad, right? So 105, what's 105? I mean, yeah. So 64 plus 32, no 16s, 18, 04, 01s. And then, of course, we have this blind radix point there. And then the question is, well, how do we convert 0.8 into binary? Well, what is 0.8? Yeah, 0.8 is 4/5, so 4 over 5 in decimal. The question was, well, what is that in binary? Okay, what did we do when we wanted to convert a decimal number into binary using division? So do you remember we used division to go left? So if division by 2 goes left in the decimal point, what would I do if I wanted to go right in the decimal point? Multiplication, right? So I could say to myself, like, okay, well, what if I so this is in base 10. What if I multiplied this by 2? So let's go ahead and look at this. So 2 times 0.8, what is that? It's 1 plus 0.6. We'll call this thing the bit, and we'll call this thing the, it's not quite the remainder. Next desired factor. Okay, so the first thing we did is we grabbed this thing, brought it down there, right? That produced 1 plus 0.6. Could you guess what we're going to do next? What's that? Which we're going to multiply by 2. Zero 0.6 times 2. What's 0.6 times 2? 1.2, which is 1 plus 0.2. We'll call this, so we'll call this the negative 1 bit, and we'll call this the negative 2 bit, because each bit that we're going to produce is going to go to the right. I guess the real question is, why can I do this, right? I don't know if I've presented a proof of that. I could definitely think about it for a second. Could you guess what we're going to do next? Each time we split the product into the leading factor plus the trailing, we take the trailing part of it and we multiply by 2. So 0.2 times 2, what's that? 0.4, which is 0 plus 0.4. Could you guess what we call this thing? Yep. What's the next thing we're going to do? Now we drop this thing down, 0.4 times 2, which is 0.8, which is 0 plus 0.8. Anybody see something very interesting right there? We start at the top, right? Okay, so just go ahead and read the string of bits to me. What's the negative 1 bit? 1, then 1, then 0, then 0, then 1. So the trailing part of this thing, so this implies, wouldn't it be a fun, would it be a fun test question if I asked you to prove why these algorithms work? I think it would be a more hard test questions than I put on the last test, right?
Yeah.
Okay, so I definitely think that makes me smile. Yeah, I can show you. I mean, I can do the one thing I could do is I could do the proof of the one that we did for integers, and then leave the proof of the one that we did for. Yeah, I'm gonna shut up for a minute. Okay, so this is 0.1100, 1100, 1100, off to infinity. What are you noticing about this? Infinite repeating, but this is really interesting because this number in base 10 has an infinite repeating decimal in base 2, but a finite exact decimal in base 10. Why was that? The denominator is not a pure power of 2, right? Okay, so this immediately, I guess let's finish that problem up first. So what did we just learn? If I wanted to encode y equals, what was it, 529 over 5? How would I do that? Well, what was the leading part of that thing? 1, 1. And then 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, all the way to infinity. What would happen if I truncate? Yeah, so the moment if I were to cut this thing, this would not be an exact representation, right? So, question, how would we check this? How would you use MATLAB to check this? What data class would allow you to check this quickly? Say it again. Yeah, so like we just made a conjecture that this number right there is that number, right? Okay, and another conjecture, this is true if and only if 4 over 5, which was 0 over 0.8, was 0.1100, 1100, 1100. Here's a claim. This is not easy. Like, it's not easy to check whether or not this happens, this is true, in MATLAB in the way that we know it right now. By next week, by the end of next week, we'll actually be able to confirm for ourselves for a base case some information about this using MATLAB's floating point precision. For now, though, we actually have to rely on something different. Think about what's being said here. How many powers of 2 are in that first bit? What's the position number of the thing right after to the right of the radix? -1. So this is 2 to the -1 plus what? 2 to the -2 plus -3, 0 times 2 to the negative. Then we've got 2 to the -5 plus 2 to the -6 plus all the way up. Do you see two different patterns? Okay, do the first set for me. 2 to the -1 plus 2 to the -5. What's next? 2 to the -9, all the way on. And then we'll add that to what? Sorry. 2 to the -2 plus 2 to the -6 plus what? 2 to the -10 plus dot, 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 dot. Okay, go ahead and write those in summation notation for me. Sum from, I don't know, perhaps we call it k equals 0 to infinity. When k is 0, what number do I want? Negative 1. So maybe I'll call this 1/2 to the 4k plus 1. Right? Okay, what's the next one? Because at 0, what's the power? 1/2. At 1, when k is 1, what's 4 times 1? 4 plus 1 is 5 on the bottom, right? Okay, what about this one? When k is 0, what power of 2 do I want on the bottom? Negative 2, and then I want it to go up by 4s. Okay, so we got to do a quick recall from last time, and then we'll take a break, and when we come back, we'll introduce fixed point notation. Do you remember the concept that if I had the sum from k goes from 0 to infinity of a times r to the k minus 1, what we said about that sum? A divided by 1 minus r. So in this case, question, can we write the first one in this format? That's called the geometric series, by the way. If you have not yet taken Math 1C, it's in Math 1C. If you have, then I'm barking up the right tree, right? How would you write that first one in that form? So I think if I pull off, how many copies of 2 would I need to pull off? So if I pull off 1/2, and then I've got 1, this is k goes from 0 to infinity, right? So I pulled off 1 copy there, and then I took the 4 in the bottom, no? Okay, what's the next one? How many copies of 1/2 would I pull off? Yeah, so this is going to be 1 over 2 squared times 1 over 2 to the 4th to the k. All right, but I need this power. If I start at 0, I need the power to be negative 1. So how many more copies of each of those do I need to pull off? 1 more, right? But I need 1 over 2 to the 4th. So this thing would be something like k goes from 0 to infinity of 1 over 2 to the 5th times 1 over 16 to the k minus 1. And then this thing would be something like what? 1 over 2 to the 6 times 1 over 16 times to the k minus 1. Here, what is my a? Yeah, and then my r is, okay, so we'll call this like a1 and a2. Using that formula up here, what does this thing converge to? 1 divided by 32 over 1 minus 1 over 16. How about this thing? 1 over 64 over 1 minus 1 over 16. So on the top I have 1 over 32. I think on the bottom I have something like 15 over 16, right? Okay.
So in the top, you said it's the top sum, the right one. You said it's 1 divided, no, top, up. Yeah, on the right. What's it's 1 divided by 2.
Oh, you're trying to figure out what that says? 2 squared. Yeah. And then the same thing's true over here. I've got something that looks like 1 over 64 divided by, I think, 15 over 16, right? What happens when I divide a fraction by another fraction? Yeah, so this is going to be 1 over 32 times 16 over 15. And then this thing is going to be 1 over 64 times 16 over 15. Let's see. So 16 divided by 32. That's 1 over 30 plus... Say it again.
1 over 60.
1 over 60. Oh, that's what you're saying. Something doesn't feel right to me about that. Three over 60 does not feel like this number to me. Oh, yeah, this should be a 1, right? Yeah, so I think this is true. So if you have the bottom index that starts at 0, that thing should start at k, right? Yeah, that makes it a lot better. In which case, this one would be just 2, right? And that one would just be 2 squared. Aha. You see it?
Yeah.
So this would be 1/2. And this would be 1 over 4. So everywhere I see this thing, so this would be 1/2, 1/4, 1/2, 1/4. Yeah, let's go real slow. So 16 divided by 2, 8 over 15. 16 divided by 4, 4 over 15. 4 plus 8, 12 over 15. What is 12 over 15? 4/5. So sadly, we are not in a space yet we can use MATLAB to, or we can understand what MATLAB is doing with this. But with one minor error, thank you, Josh, for converging on that, we can confirm that the algorithm that we supposed actually does produce the number that we want. Let us take a break now. When we come back from break, we'll introduce the last bit of what you might call binary representations, and then when we start the next part of this session, we'll start introducing the concept of fixed points upon which floating points is built. So it is now 10:55. We'll start again at 11:05. Awesome. All right, see you in just a minute.